estimation. We don't learn many algorithms. I spend the time very slowly, right? So actually this semester I will talk about phase estimation. In the past, I don't talk about phase estimation, but I spend a lot of time to derive the circuit for quantum Fourier transform, which is very confusing. I think it's not necessary for this level. So I will skip that part about deriving the circuit for quantum Fourier transform, but replace it by phase estimation. Quantum phase estimation is very useful for more advanced algorithm, including Shor's algorithm, including the HHL, which you can use to have exponential speed up on solving system of linear equation. Okay. So before we go into the quantum Fourier transform, we need to review some of the complex number basics. Okay. First of all, what is E? What is e to the power I theta? Right? We know that this is a complex number, is represented on a complex plane. Horizontal axis is real, vertical axis is imaginary. Any point here, like C, is equal to A plus BI. Is that okay? Right? A plus BI. But there's another way to represent it, right? It is equal to, maybe I should just do this, right? C is like a vector. C equals to A plus BI. And C actually is also equal to the magnitude of C times e to the power I theta, right? But again, in this class, we only care about, normalized vector or the vector magnitude. So you can imagine we probably only care about the complex number with only modulus equal to 1, the size equal to 1, right? So C is going to be 1. So that's why e to the I theta is what we are interested in, right? How do we express it in the form of A plus BI for e? Very good. Cosine theta plus I sine theta. You all know that, but I need to repeat, and you need to make sure that you know that, right? Now, what if, so basically, if it is only a unity, then it's going to be on this circle, right? So, of course, if I go through this circle one more time, it is still myself, right? So you can imagine what is e to the power I 2 pi theta. Of course, it's equals to cosine 2 pi. Can I say 2 pi theta?
Is it 2 pi plus?
So sorry, I say the wrong thing. That is not what I want to say. I completely, my cheat sheet has problem. What is 2 pi times k if k is integer? If k is integer, right? Is equal to cosine 2 pi k plus I sine 2 pi k, right? What is this? Say again. Someone say 1, right? Because 2 pi, cosine 2 pi is 1, sine 2 pi is 0, and if you're k, they are still the same, right? So my question to you is, if I have a complex number, is power to the n is an integer equals to 1, what is x? Right? And that is the nth root of unity. And what is x? X equals to e to the power I 2 pi k divided by n, with k equals to 0, 1, 2, all the way to n minus 1, right? So 1, we always just, in the real domain, 1 to the power 1 over n, you take nth root is still 1, right? We usually don't think about the complex number. But indeed, if it is in the complex domain, the nth root of 1 actually have nth root. And these are shown here. This is when n equals to 12. So what does it mean? It has the k equal to 0, then it is 1, right? 1 to the power 12 is 1. But it can also have k equal to 1, right? So what is that? For example, when n equal to 12, k equal to 1, then x equal to I 2 pi divide, e to the power. E to the power I 2 pi divided by 12, right? And we are going to call this omega. And after that, it's just omega 2, omega to the power 3, omega to the power 4 when you keep multiplying by k, right? So in general, right, x equals to omega 0, omega to the power 1, omega to the power 2, all the way to the omega to the power n minus 1 with omega equal to e to the power I 2 pi divided by n. Okay, so I need you to memorize this equation, which is not difficult. That's what I want to review as the first step. Yeah.
Did you just pick 12 arbitrarily, or did that come from somewhere?
No, just arbitrarily, because in order to draw this figure, 12 looks is the best. Otherwise, too dense. Yeah. Yeah. So you really recognize what is omega to the power n. You will just come back, right? For example, omega to the power 12, it becomes omega 0. You keep stepping forward when you increase the index, right? So I hope you have this mentality, right? If n equal to 2, means what is square root 1? It can be 1 or negative 1, because each time it has a big step, half circle. Okay? Any questions? But most important is this equation, right? You need to be very familiar with this. Of course, you understand, but if you're not familiar, it's difficult to deal with complex stuff. Omega equal to e to the power I 2 pi divided by n. Okay? Okay. Now, then we continue to look at the property of this omega. The first property is this. What is omega 0 plus omega 1 plus omega 2 all the way to omega n minus 1? Basically, I say sum up all the nth roots of unity. Sum them up, right? What is that? So this one, you can try it, but maybe you probably forgot we can use the sum of a geometric series. Because each of them, if you remember, that is what we learned, right, in previous class, maybe times ax plus a square x, right, plus a to power n x, for example, geometric series is equal to what? 1 minus the ratio. The ratio is a for each series, and number of terms, let me call this n minus 1. Then you have 1 minus a divided by 1 minus a, right? 1 minus a to the power n divided by 1 minus a. Now, this one, if you forgot, no worry, right? Google. Same here. What is the first term in this? So this is x, I'm sorry, actually. This should be x. The first term is x, not a, right? Yeah, I don't know why I said x, but we can just use 1. What is the first term? Here. Omega 0, right? Minus, what is the ratio of the term? Each term, what is the ratio? What is omega 1 divided by omega 0? Omega to the power 1 divided, omega, right? Omega 2 divided by omega 1 omega, right? So the ratio is omega, but I have n terms. And the bottom is omega 0 minus omega, right? What is omega 0? Omega to the power 0. 1, right? It's 1. Omega 0 is here. This is 1. So this is 1 minus omega to the power n divided 1 minus omega. If n is larger than 1, no, sorry, say the wrong thing. What is omega to the power n? I forgot to do this. What is omega to the power n? Look. We just got from the previous slide. What is omega to the power n? Let me check. Omega to the power n equals to e to the power I 2 pi divided by n times n, which is e to the power I 2 pi. What is this? 1, right? So this is what? 0. And that makes sense because omega to the power 12 is omega, is 1, right? In this example, you keep looping, right? This is n minus 1, and then you become n, omega to the power n. And what does this make sense? It means you add all these points together, it becomes 0. Does this make sense graphically? Yeah, because it's symmetric, right? Positive cancel negative, right? Imaginary part cancel imaginary part. So it makes sense, just like the vector. What would you call this, by the way? Destructive interference. If in the quantum computer you come up with this nth root of unity and you add them together due to something, and that is quantum Fourier transform, a row of them, you get destructive interference. That term will be gone because you don't want that solution. Okay, so this is the first property. You need to memorize it. Okay, now second property is for an integer L. Okay, I give you any integer. Now this time I'm trying to do this. Omega L times 0 plus omega L1, or maybe I should rewrite it. Omega to the power 0 to the power L to the power 1 to the power L, all the way to omega n minus 1 to the power L. Add them together. What would that be? This would be even more interesting. We still use the sum of geometric series. The first term is omega 0 to the power L. What is the ratio again between these terms? Still omega, right? Because all of them just get to the power L, right? Or wrong? Or no? Actually, I say it wrong. Let's try it, right? For example, what is omega 1L divided by omega 0L? Is 0 omega 1L minus 0L equal to omega 1L? Right? So their ratio is omega L, omega to the power L. And the number of terms is n, right? This is just following the geometric series equation, right? I need to multiply to the power n. And then the denominator is just omega to the power 0L, the first term, minus the ratio. Okay? What is this? This is 1 minus omega to the power n to the power L divided by 1 minus omega L. Okay? And I was too fast. Actually, I was too fast. If I can write this, we assume, here I assume that this one, assume L not equal to 0. Because if L equal to 0, it will be 1 minus 0, right? And then this is also 1 minus 1. I mean, 1 minus 1 and 1 minus 1, 0 divided by 0, right? So this is when L not equal to 0. When L is not equal to 0, then the denominator is non-zero, but the numerator is 0, correct? Because omega to the power n is 1. 1 to the power L is still 1. So 1 minus 1 is 0. Again, everything is gone. Okay? I call this destructive interference. Destructive interference. Is that okay? But what if omega, what if L equal to 0? Then this one becomes 1 plus 1 plus 1 all the way to 1. Because L is 0. How many 1 do we have? N. Very strong signal. This is constructive interference. Right? We don't need to go to quantum mechanics. We don't need to study wave. We use this already just by this algebra. Okay, so the sum, if you have this term, the envelope of unity raised to the power L and you add them together, depends on the value of L, you can get constructive or destructive interference. These are the tools for you to develop the quantum algorithm. Because I want to extract certain things, let me mix them together, do some quantum Fourier transform, and I hope that I will just make those long answers 0. And only the states I'm looking at has the largest peak. And then when I measure, I'm sure that I'm getting the answer I want. Okay, you will understand later. It's still not clear to you. But I want you to bear this in mind. And finally, the last property that we want to review is what is omega n minus 1 equal to omega minus 1? Okay, just this is not that difficult. What is n minus 1 in this case when it's 12? 11, right? So I step 11 step is the same as I step negative 1 step. That's it. That is just to show you the nature, but it's easy to prove. Omega n minus 1 equals to e to the power I 2 pi divided by n, because this is what omega is about, times n minus 1. I expand it, becomes e to the power I 2 pi n times n times I to the power 2 pi e to the power I 2 pi n minus 1, right? That is just the rule. When you multiply them, the index will add together. What is the first term? What is that? E to the power 2 pi n times n. It's 1. But n cancel. E to the power I 2 pi is 1. And of course, then this is equal to negative, negative I 2 pi divided by n, which is omega to the power negative 1. Okay? So all this actually graphically we already understand. Add all them together, destructive interference 0. Stepping forward by so much step is equal to stepping backward by n minus so much step. And then when this is more special, when your L is larger than 1, again destructive, but if you can make it equal to 0, then you just add them together. Okay? So we are done with the basic math. The next thing we'll review is the so-called discrete Fourier transform, right? The signal processing. But don't worry if you forget about it, because we only look at the very simple aspect. But why I want to do that? Because quantum Fourier transform is exactly the same as discrete Fourier transform. Yes. Constructive is difficult to explain from here, but basically you can see that if the angle is so large, every step you go through 360 degrees, then you have constructive. Later you will see in Shor's algorithm it's like that.
Well, but yeah, if you make a full circle, come back to the same point.
Yeah.
Constructive.
Then it's constructive. Because after one circle, right, you come back to the same place. After another circle, you come back to the same place. And then you add all of them together, then it's constructive. Yeah, but if you distribute evenly after some step, right, and then eventually you fill up the whole circle, they all got cancelled when you add them together. Right? You add all these points together, it is 0. Make sense? Okay. You will appreciate more later in the Shor's algorithm, but just remember this, okay? So what is discrete Fourier transform? It is very easy, okay? We define a vector. And a vector can be multidimensional. It has many components, x1, x0, all the way to xn minus 1. What is the dimension of this vector? N, right? Because I have n component. And it has its basis states. I did not say what is its basis state. It can be the English alphabet. It can be the quantum basis state, actually, right? I do a Fourier transformation, discrete Fourier transform. This is sometimes confuse the device guy. They will say this is density functional theory, DFT. Yeah. Then I get the output. Input becomes the output. Y0, Y1, all the way to Yn minus 1. That's it. That is discrete Fourier transform. Okay, you come up with a matrix. You convert this vector to another vector. That is discrete Fourier transform. But of course, it is the matrix nature define what is a discrete Fourier transform. Okay, you cannot come up with arbitrary matrix. And we define. Sorry, it's not define a vector. It's given a vector. Given. Okay. We define what? We say the k components of the output equals to 1 over square root capital N, the dimension, summation j equal to 0 to n minus 1 times xj times e to the power negative I 2 pi divided by n k times j. Now, I hope that now you start seeing that how it's related to the nth root of unity. Basically, what you say is your k component come from the contribution of all the initial components, all the components of the input vector. And how much contribution do they have? It depends on the weight. And what is the weight? Is this the nth root of unity to the power k times j? Okay, let me write it clearly. Equals to 1 over square root n, summation j equal to 0, n minus 1, xj omega negative kj, right? Because omega is I 2 pi divided by n, e to the I 2 pi divided by n, right? Let's see again what I say is correct. If I want to find the k component in the output, you find what is the 0th component times omega to the power negative k times 0 plus x1 omega to the power negative k times 1, right? Maybe the best is to give you a numerical example. I thought I had this in the assignment, right? For example, y12 equals to 1 over square root n x0 times omega negative 0 times 12 plus x1 omega negative 1 times 12 plus x2 omega negative 2 times 12 all the way to n minus 1 omega negative n minus 1 times 12. I don't want to write it, I don't have space, but you know what I mean, right? Is this okay? That is a discrete Fourier transform. I want you to have to appreciate what we're talking about, right? Input has a vector. Every component contribute to the final vector output, right? But how much does it contribute? It depends on the index and what output you're talking about. Which output is omega to the power negative k times j, okay? How do you write this in a matrix? You need to trust me, and you can try it yourself to verify. This is the output vector, y0, y1, all the way to yn minus 1. And the matrix is going to be 1 over square root n, omega negative 0 times 0, omega negative 0 times 1, omega, and then let me skip this, dot, 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 omega negative 0 times n minus 1 as the first row. Second row, negative 1 dot 0, negative 1 dot 1, dot, 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 omega negative 1 dot n minus 1. Basically, it's talking each element, it is omega to the power negative row number times column number. You keep doing this, you get omega negative n minus 1 dot 0, omega negative n minus 1 dot 1, because it's the nth minus 1th row, the last row, times 0 or 1 column, right? What is the last one? Negative n minus 1 times n minus 1. This whole thing times x0, x1, all the way to x n minus 1. Although it is messy, but actually this helps you to memorize. You can just verify. For example, the first or the 12, right? The first, if this is the first, y0 equal to this row times this column, right? So this row is what? Like k is all 1. And then 0 map to 0, 1 map to 1, n minus 1 map to n minus 1. And that is exactly what we have here as the definition. Okay, so now I hope it helps you to memorize. The discrete Fourier transform is so easy. It is basically y equals to 1 over square root n, and then I just say the inside is omega negative k times j times x. It says that each element in this matrix is omega to the power negative kj, where k is the row and j is the column. Okay, depends on which row, which column you're asking, put in omega to the power negative kj. Is this okay? I don't know if you still remember discrete Fourier transform. I learned it many years ago in undergrad, right? And I feel that it's a very difficult thing indeed, a lot of useful thing. But now you look back, it's easy if you use this definition. You just transform one vector to another vector. And how does it transform? Just use omega to the power negative kj. And what is omega? The nth root unity of unity. E to the power negative I2 pi over n. Okay? So why I spend so much time? I still have example. Yeah, it would be good to appreciate the constructive and destructive interference, right? So I can say y0, y1, all the way to yn minus 1, like what I say last time. Now I'm going to write it in this way. 1, 1, 1, 1, 1. Why? Why is all 1 for the first row and the first column? Yeah, very good. Because we have 0 here, it's all omega to the power 0, omega to the power 0. And then how about the next one? You just multiply by another more omega, right? When you're adjacent to each other. So this is omega to the power negative 1. Omega to the power negative 2. All the way to omega to the power negative n minus 1. And this is going omega negative n minus 1 for the last row, right? And then all the way to omega negative n minus 1, n minus 1. Right here, it just be more elaborate. x0, x1, xn minus 1. Now, question to you. On top, I have an input signal. This can be a time domain voltage signal. I want to find the discrete Fourier transform of it. This time domain is a constant, right? So basically, it is equal to 1 over n, the whole thing. But I have what? 1, 1, 1, 1. Every term is 1. What is y0? What is the y0? 1 over square root n times 1 plus 1 all the way to 1, which is equals to, I think I did something wrong again. Okay, sorry. This one need to have a square root n because I need to normalize the vector. Okay, I still have one more square root n that I'm missing. The vector itself, I cannot have the entry with all 1. The entry should be 1 over n, 1 over square root n, 1 over square root n. So I have a normalized vector. Okay. So basically what I'm saying is this. Here is 1 over square root n, the amplitude of each component. So this one will be equals to 1, right? So my first component is 1. Is this okay? Makes sense, right? Exactly. It's just DC. DC signal in time domain, discrete Fourier in frequency domain, F0 should be large. And then others should be 0, right? Is that right? What if I have y to the power k, right? So we follow what we learned earlier. We know that this is equal to 1 over square root n, and you do the multiplication. It is equal to omega, we're talking about k, right? With k not equal to 0 times what? Times 0, because it's all 1, right? Plus omega negative k times 1, plus omega negative k times 2, all the way to omega negative k times n minus 1, right? If I, for example, when k is equal to 1, is this times this, this times this, this times this, right? But what is this? We just learned this equation. This is nth root of unity. You add them together, except that each of them is raised to the power k. That is this equation, right? Nth root of unity, you add them together, but each term raised to the power I. But I not equal to 0. Here, k not equal to 0. What do you get? 0. And that's why I want to show you why this quantum Fourier transform can achieve, this discrete Fourier transform can achieve constructive and destructive interference. This is a good example, right? So you remember when you do time domain to frequency domain conversion, you are already doing the constructive and destructive interference. And that's why your DC signal gives you only one component in the frequency domain. Yeah. Well, yeah, they're very good, right? So he say each row is for one frequency component, and you try to scan, right? It's just like sampling. You sample the first one by this weight, the second one by this way. So each row corresponds to one frequency. Here we are talking about time to frequency, but this is not necessary. They don't need to be time and frequency. They even can have the same basis, and that is the case in quantum computing. They are still the basis state. Yeah, question? This one? Oh, because, sorry, this is a typo. 1 over square root n. Very good, yeah. Okay, good. Why we spend so much time for what? Because quantum Fourier transform is very easy. It's just the same. It defined in this way. First of all, you must be a unitary gate. Anything quantum computing need to be unitary. And it is nothing but just equals to exactly the same as the discrete Fourier transform. Okay, in terms of equation. Now, however, this is my terminology. I call this quantum Fourier transform. Quite some book will call this inverse quantum Fourier transform. The only difference is just because of negative sign. I will show you that it doesn't matter. You just need to pick one of them, right? But now for this class, let's do this first. Later, when we are doing inverse quantum Fourier transform, then I will remind you again. Okay? Just be careful of that. So that's it. This is, and again, this is a matrix, right? I just showed the element. It's talking about the kth row and jth column element is omega to the power negative kj. Is that okay? Exactly the same, right? So I am going to write this out as e to the power negative 2 pi I divided by n kj, nth roots of unity. Okay? Maybe I remind you now. Some places call this inverse quantum Fourier transform, IQFT. Quantum Fourier transform is QFT. Everything is, you can read my book. I give some explanation why they are different names. I'm not the only one calling in this way, okay? And the reason I call it this way is because this is just exactly the same as the discrete Fourier transform. But they call in another way is related to rotation of the vector, which we don't have time to go to too much detail. But you read my book, I make it pretty clear, right? So because of this, right, then let's take a look. Maybe because although it's exactly the same, it would be good to just do write this out, right? So which is equals to, I just write it out, 1 over square root n, 1, 1, 1, right? Everywhere is 1. And then e to the power negative 2 pi I divided by n, right? All the way to e to the power negative 2 pi I divided by n times n minus 1, right? And this diagonal is e to the power negative 2 pi I divided by n, which is omega to the power negative 1 times n minus 1 times n minus 1. Nothing special, the same as the matrix we see earlier. Exactly the same as discrete Fourier transform, okay? Now, let's see how it operates on a basis state. If I apply quantum Fourier transform matrix to J, okay, J is a basis state, right? How do we represent it in the column form? Very good. 0, 0, all the way to 1, not J, 0, but this is the jth row, right? Jth row. If you look at this, right, when you do a multiplication, what does this multiplication do? It will going to take out the jth column of the matrix, right? Which is equal to 1 over square root n e to the power not E, I would use omega actually. Omega to the power negative 0j, because it's the first row, jth column. Omega to the power negative 1j, second row, first jth column, all the way to omega to the power negative n minus 1j. Right? This is just the jth column of the quantum Fourier transform matrix. So when you do this, you get that, right? When you apply the quantum Fourier transform into one basis vector. Now, this is the confusing part, why I want to do that. Then, what is this? Isn't that is equal to 1 over square root n? And then omega 0 times j 1, 0, 0 plus omega negative 1 times j 0, 1, 0 plus all the way to omega negative n minus 1 times j 0, 0, 1. Do you agree? In the bracket notation, what is the first column? What do we call it? The first, this one, 1, 0, 0, 0. In bracket notation, what is that? That is the 0 vector, right? This is the 1 vector, right? This is the n minus 1 vector, right? So this one is just equal to 1 over square root n summation, let me call it k equal to 0 n minus 1 k. Yes, not E, omega, you're right. Omega negative j dot k. Now, this is always something confused myself. It's myself that got confused. And that's why it also called inverse quantum Fourier transform in some case. You look at, I apply to a basis vector, it becomes a linear combination of all the basis vector weighted by this. Now, if you look back to the discrete Fourier transformation, we see the coefficient is equal to the linear combination of the coefficient of the input vector. This confusion comes from the fact that you are doing different type of rotation. That one is rotating the coordinates, another is rotating the vector. But don't get confused. Don't worry about this. I just want you to be aware of this. Is one day when you're deriving equation reading paper, you see this one applied to J becomes a combination of other vector. That is very normal. That is how it works. Okay, and you can come back to here, right? But the property of the quantum Fourier transform applied to the jth basis vector is to take out the jth column of the quantum Fourier transform matrix, which is equal to a linear combination of all the basis vector weighted by omega to the power negative jk. Okay, this is one equation you will use a lot in, let's say, HHL. Any questions? Yeah. Exactly. You do a quantum Fourier transforming on a basis vector, it becomes a superposition of other vectors with a certain weighting, which is normal. Basically, just saying that you rotate your vector and then it